Hey everybody, in this lesson we're going to talk about significant figures. Significant figures allows us to represent a value as precise and accurate as possible. So first of all, before we even talk about significant figures, we got to talk about what is accuracy and precision and their difference. Well, we know that you always want to measure something to the accepted value. So accepted is what you expect to get. Okay? So accuracy is getting the accepted value. Precision, on the other hand, is having more decimals. Now, why is that if you have more decimals, you are more precise? So, think about it in terms of sports, okay? If you're accurate in, for example, hockey, you can hit a corner, for example, really, really well. So you could pick a corner in a net, and you could hit that spot every time. Precision is if you could, for example, hit the goalpost every single time you shoot. Now, how does that deal with more decimal places? Well, the more precise an instrument is, that means it's able to reproduce that more often. If it's able to do that, it's going to have more decimal places. So an example of that is if Mr. Chill weighs 72.351355 kilograms exactly, then what does each of these values represent if you were to find them? Okay, so what this means here is if this is the accepted value, what does each of these mean? Well, for the 72.35 kilograms, this is it accurate? Yeah, it is. I would say it's accurate, but it's not precise because it doesn't have a lot of decimal places. Why is it accurate? Well, I am 72.35 kilograms, but I have a bit more decimals after that. If the scale was to give you that value, it's accurate. That scale is accurate. It's just not precise yet. Okay, 74.32345 kilograms. This one is it accurate? No, it's not accurate because it doesn't give you close to the accepted value. But because it gives you a lot of decimal places, this scale is pretty sure of its value. Because it's pretty sure of its value, because it's hitting that same spot every time, this is actually precise. Okay, what about 72.35113 kilograms? In this case, this one is accurate and precise because it's getting pretty much the accepted value. And if it's reading 82.2 kilograms, this is not accurate and it's not precise. Now you can think of it in terms of this image here, accuracy and precision. If this is a bullseye and you are shooting at this bullseye and you're hitting it all these random spots, you're not accurate because that's where you want to hit, and you're not precise because you're not hitting it in one region. This next one over here to the right, this one is not accurate because you're not hitting the bullseye, but it's actually precise because you're able to hit that same region every time. So this is an example of getting a lot of decimal places. This one, you're hitting a lot at the bullseye, so you're pretty accurate, but you're not grouping your shots, so you're not precise. So this one will be a low amount of decimals. This one is high accuracy because you're hitting the bullseye, and highly precise. So this one will be something that is accepted value with lots of decimal places. So going over accuracy and precision, what does this have to do with significant figures? Well, what this has to do with significant figures is it is a figure or value that is accurate and precise. Okay? So what this means, it's the value you can trust without error in a sense. And this is because a lot of tools have some sort of uncertainty. So it's basically the value that you can trust. Now, we call this thing sig fig for short. Okay, sig fig for short. Now, why do we have significant figures? Why do we have some values that we could trust and others we cannot? Let's look at this example. Okay, we trust our calculator way too much, for example. Okay, let's say, for example, um, a scale reads, let's say, for example, 75 point, let's say 4 kilograms. Okay, let's say that's a scale. It reads that value. Can you trust that this scale is correct? Because this 75.4 kilograms can be any value of 75.3 5 0 0 0 0 dot, right? Because you round up to 75.44444 dot. See that huge range of value? There's an infinite amount of numbers that could fit between these two numbers. Because it's infinite, we can't actually trust any number after that 4. We just can't. So what this means is that the 75.4 kilograms is significant because we can trust it. We cannot assume any other digit or value. So you might go, well, this is accurate, but it's not really precise. It doesn't have many decimal places, but it's as precise as we can make it to be. Yeah, if you put more and more decimal places, for example, you put 75.44444 repeating, you might go, there's more precision, but you're losing accuracy. Significant figure is something that is both accurate and precise. It's a fine balancing act. So you want it to be as accurate and precise as possible. So just because if you put more decimal places, you might increase precision, but you're decreasing accuracy. So that is why 75.4 kilograms in this case is the most significant you can have, the most accurate and precise you can have. Now with this comes a bit of rules. There's a bit of rules that talks about what and how many significant figures something has. So these are the rules we're going to talk about. There's 4 of them. The first rule, all non-zero digits are significant. What that means is any number that's not a 0 is significant if it's presented. Why do we not trust zeros then? It's because zeros is something we always round to. So say for example, if you have 75,000, we know it's 75,000, but that 000 at the end can be rounded. We don't know. Number 2, zeros between non-zero digits are significant. So what that means is this. Let's first of all talk about 75,000 again. In this case, not 75,000. Let's talk about 75,410, or no, 411. All 5 of these numbers are significant because you could trust every one of those values. But if you look at, for example, this rule number 2, 75,002. These zeros are actually significant because that 2 makes these zeros significant because that 2 is trusted. So it also makes these zeros trusted. They are zeros. They're not anything that's been rounded. Okay, rule number 3. Zeros before a non-zero digit are not significant. I'll explain to you what this one means. What this one means is if you have 0.075, these zeros here are not significant. Now you're going, wait, those are zeros. How can they be not significant? The reason why they're not significant is because you could represent this 0.075 as scientific notation. And that's why only the 7 and the 5 are significant. Okay, the last rule. Zeros after a non-zero digit are only significant if a decimal is present. Okay, what does this one mean? Well, let's look at these two numbers. If you have, let's say, 75 point, let's say 750.0 versus 750. Okay, if you look at these right here, these zeros are significant. They are significant. Why? Because this decimal proves that this is a zero. You could actually trust that this is a zero because of the decimal. The decimal tells you that that is a zero. That may not be a zero. This 750 could have been rounded. It could have been 749. It could have been 751. So you cannot assume that this is 750. So that's why only these two numbers here are significant. That zero is not significant. So that's a big difference. Here, these zeros are significant. While this one, this zero, is not significant. So let's look at these examples here then. If you look at these examples right here, let's see which of these, or how many sig figs each of these has. So the first one is 2000. 2000 only has one sig fig, or SF for short, because this is trusted to be a 2, but these zeros afterwards may not be zeros. This could have been rounded to 2000. But the next one is 2000 decimal. And the moment there's a decimal there, these zeros can now be trusted. So that's why there's 4 sig figs, because these are actually zeros. That decimal proves that they are zeros. 0.001 is the next one. That one is 1 sig fig, because these zeros before are not significant, because you put this in scientific notation. 2002. This one is 4 sig figs, because you can prove these are zeros because it's 2 makes these zeros trusted. 2330. This one is 3 sig figs, because this 0 at the end could have been rounded. 200000000. I think 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 2. This one is 9 sig figs, because this 2 here makes all these zeros zeros. It proves that they are zeros. They're not rounded. 23.00. This one is 4 sig figs, because this decimal, again, there's a decimal, proves that these zeros are significant. So how does scientific notation work for sig figs then? Well, we follow the same rule. Okay, except for the 10 to the power of x are zeros. So remember, that 10 to the power of something is a 0. They're all zeros, so they're not significant. So for example, 2.95 times 10 to the power of 3, this is 3 sig figs, because that is not significant. Okay, and if you were to write this out, this number is 2950. That is why. That 0 right there is not significant, because you cannot trust that that is a 0. It could have been a 1. It could have been 2. It has been rounded, for example. The last thing we're talking about here is how do we round 3.65 or any number that ends in 5? Because we're always taught when we have a number that ends in a 5, we want to round it to the next digit beside the 5. We used to round it up, don't we? So we always round 3.65 up to 3.7. But this is wrong. Why is that? Because, let's look at it. If you're rounding 1, 2, 3, and 4 down, but you're rounding 5, 6, 7, 8, and 9 up, you end up seeing that you round 5 digits up, but only 4 digits down. And what that ends up happening is you round up more than down. So with one number, that might not be a problem, but when you're multiplying multiple things over a long period of time, that could skew your data upwards. So that is an issue. So it's bad for data. So there's something called the Rule of 5. In this class, we're going to use the Rule of 5 in that this is what the Rule of 5 states. If you are rounding a value that is ending a 5 to the number beside it, round to the even number. So what you get is 3.65. If you round that 5 to the next value, which is 6, this one will round down to 3.6. You want to round to the even number. So now what ends up happening is 5 isn't just going to be rounded up always. It could also be rounded down half the amount of times. So instead of having 5 digits to round up, now you have, in a sense, 4.5 digits that round up. And because 5 can also be rounded down now, you have 4.5 digits that round down as well. So let's look at this in action. Let's round the following to the nearest hundreds, for example. So that means we want to round it to this number and this number. So 3.775, well, this 5, look at the next number. That is a 7. When that is a 7, that's an odd number. We want to round this number to an even number, 3.78. So we don't round it down this time. We want to round it up. For 29.445, we want to round this number to the number there, so beside it, to the hundreds. In this case, we want to round this one down to an even number because it's even. So both of these values are, as you can see, even. So, as always, make sure you keep yourself safe and healthy, and I'll see you soon.